in different situations. So then the first question which scientists begin to ask after some time that can we circumvent such situation? Is it possible for us to circumvent such situation? So can we leverage related unannotated data set to reduce the need of annotated data set? So let me just tell you that see, there is a lot of unannotated data sets, like there is a lot of stories in internet. Okay, there are Wikipedia pages, but there are less amount of annotated data set. Like, what does annotated data set means? Annotated data set means that if you have mm, if you have a document and a corresponding annotation whether this document is expressing positive sentiment, negative sentiment, or neutral sentiment. So this type of annotated documents are very less, but there is a lot of document out there in the internet. So the question is, can we leverage related unannotated data set to reduce the need of annotated data? So if we can understand the semantics of unannotated data, it will quickly help in performing a specific task. So if we can understand the semantics of this unannotated data, if we see it again and again and again and again, we may be able to understand the semantics of unannotated data, and that would help us quickly perform a specific task like classification, prediction, sentiment analysis, as I was telling, sentiment analysis. So take this example. So if you read a lot of story books, it helps you to enable write good essays. Okay. So see, think of this simple thing which you may have all done during your childhood days, that if you have to write good essays, your teachers, your parents may have told read books so that you can write good essays. So note, the first task is completely independent of the second task. So there may be a lot of people who are reading a lot of story books but never writing essays. So it is not mandatory that if you read story books, you have to write good essays. Okay, or you have to write essays. Okay, it is not mandatory. So the first task is completely independent of the second task. So that's why this is called pre-training. Okay, it's not training, it is pre-training because it is completely independent of the task at hand. And now let us see how pre-training works. Okay, it is working on a very simple task of self-supervision. So what is this self-supervision? Say you have this, the quick brown fox jumps over the lazy dog. And you do a simple thing, you mask. Okay, mask, quick brown mask jumps over the lazy dog and tell the machine to guess. Okay, what is it? If the machine guesses rightly, you give some bonus, or you give some prize, and if the machine doesn't guess rightly, you penalize the machine. And you go on doing this for millions and millions and even trillions of data and billions of sentences. As you go on doing this again and again and again, the simple task, very simple task. I hope all of you have understood this simple task, very simple task. Then suddenly machine begins to understand the semantics of the English language. Okay, it begins to understand the semantics of English language. So you can think of something like, so I am guessing all of you are from Goa. So something like a outsider auto wala coming to Goa, and listening, he begins to understand the local language of Goa. So it is just listening and trying to tell, making some mistake, telling again, making a mistake, and you are learning. So this is how we can leverage, and this is how pre-training works. Okay. So this is what we called, you may have heard this now, mask language model, because masking some of the words and then trying to guess it. Okay. So we have performed this on millions and billions of data set, and we gain some sort of understanding. And once we gain some sort of understanding, use this understanding to perform specific tasks. So once you begin to understand the local language of Goa, then you begin to understand whether this guy is talking good about you, bad about you. So there is a tone part, but if you forget the tone, whether this person is good, is expressing positive sentiment or negative sentiment or just business like neutral sentiment. So then you are at a much better position to perform certain domain specific tasks. Okay, I guess I am giving you the perspective clearly. So see, there is a huge need of it even after the emergence of LLM. There is abundance in domain specific NLP applications. Okay, so we have generic applications, that how to um, plan 5 days in Goa. Okay, so this may be a very generic applications, but there may be very domain specific NLP applications. Like say you are taking electronics gadgets and they need customer support, and they have some question answering like how can I encrypt my SD card. Okay, then you have to give an answer. Or if you think about legal cases, there can be clause span extraction, that what is the clause which we should argue on. So this is about legal domain. Or you can have financial domains, that where you are trying to see that what is this number means. Okay. What is this number means? The dollar 24.8 million. Okay. So dollar 24.8 million may mean cash and cash equivalent, while dollar 18.2 means debt instrument convertible conversion price. So this sort of things we need to understand, which is called named entity recognition in a broader sense. Or in biomedical domain, there are various tasks like named entity recognition. You have to understand relations, relation extraction. You have the question answering, and this sort of different sort of tasks are there. So in the new domain of NLP, they are trying to actually conquer all these tasks, all these very specific tasks which are difficult to understand, and difficult to understand or difficult to even decipher by humans. Humans also need a lot of education training to do these tasks. Okay. So, but what are the issues also? See, the domain specific data set, unlike say CNN Daily Mail, there is a lot of data sets. Okay, this is a generic data set. Wikipedia, there is data set, but in domain specific data sets, they are often small in size and they are costly to make, as heavy domain expertise is needed. So, if you think that you will make a question answering you will make a question answering data set, you will make a question answering data set using you will make a question answering data set uh, for e-manuals, okay, which is very difficult because there may be some experts on say fridge, refrigerators, there may be some experts on mobile phone, there may be some experts on television. So you have to bring in all this sort of people, all this sort of domain experts to actually do this. Okay. And otherwise, the other thing which people do is crowdsourcing. Okay. And crowdsourcing here is very unreliable. Okay. I always give a interesting example here. So many of you have perhaps seen who कौन बनेगा करोड़पति. Okay, you have seen कौन बनेगा करोड़पति. So, and you know audience choice is a option. Audience choice is a option. Now, if you think carefully, audience choice works perfectly when the questions are easy. So in the first 10 questions, audience choice works. But as soon as questions become difficult, audience choice doesn't work. So this is the thing, that when you can not solve it through crowdsourcing, because crowd don't have the knowledge. So bringing in more crowd really doesn't solve the problem. You actually need heavy domain experts. Okay, so this is what the situation is. So the point is, that's why we need to leverage this available unlabeled or silver level data, right? So that's why the pre-training thing becomes so important, or what we can call it is continual training, because anyway there is a pre-training which has happened. Say now we are talking about ChatGPT, etc. So there is a sort of pre-training which has happened, but you have to pre-train over that, and that is called continual pre-training. Okay. So this is first thing I will tell you, that I can tell you this problem. Let me tell you this problem. So this is question answering over electronic devices. So the question is, how can I encrypt my SD card? This is a good question, but this question this question are complex and these are multi-aspect. Like I'm taking another question, how can I save my selfies without flipping them? And what's the answer? The answers are multi-sentence. Okay, there are not. It's not in a single sentence. You cannot find in a manual in a single sentence. These are multi-sentence, non-contiguous. They are not in a one space, and they are multi-spans. Okay, it spans in multiple level. There is one span here, one span here, one span here. So there are multi-spans. So this is a complex question. So what I'm just trying to understand, trying to tell you, and just keep this in mind, these are complex multi-aspect questions, okay, which cannot be answered like, who is the president of India? That is a simple question, okay, it's a one-shot question answer. But these are very complex questions, and finding out through a standard IR technique, is next to impossible. So if you fire this question on Google, what will Google do? Google will at most point to the relevant pages. But inside that relevant pages, then you have to have real expertise and real patience to find out how to get the answers. Okay. So what we did, we actually took a multitask approach. Okay, we took a multitask learning approach. So there are two things which we need. One is the section prediction. So we have to have the section, in which section of the e-manual will get the answer, and the answer prediction, that exactly where are the answers. So this is a two-step process. We have to get the section and we have to get the answer from that section. And that answer has multiple span. Okay. And what we did, see, section prediction, it can be a sequential step, that you do the section prediction first and then do the answer prediction. But we framed it as a multitask learning, whereby although this is a sequential thing, section prediction was learning from answer prediction and answer prediction was learning from section prediction. So this is, that way the reviewers told that this is a very novel approach. Okay, but as soon as you take novel approach, and as soon as you try to get informations or learning from one section to another section, the basic bottleneck is that there is a lot of data needed. Because if you see this thing, this architecture, this neural network or this neural network, the initially it is random weights. So this neural network has to be updated to really make it learn. And if we have to make it learn this complex architecture, then it requires a lot of data set. Okay, so what we told, that see, we don't have a lot of data sets. Okay, for a particular question. But we saw that there are a lot of e-manuals in the internet. So like the student found that there are at least 300,000 e-manuals in the internet. And why don't we scan and why don't we crawl all those e-manuals to ourselves? So we crawled all those e-manuals and then did a pre-training. Okay, then did a pre-training, and this pre-training weights were transferred to this machine. Okay, transferred to this neural network. So the neural network and how was the pre-training done? The pre-training was done by very simple. The defroster can be found at XX end of the refrigerator, and you are writing that defroster can be found at the top end of the refrigerator. Okay, so this is how we proceeded. This is how we proceeded, and what we did now, it is not starting from random weights, it is starting from weights obtained from pre-training. So in that way, you are taking this task a little bit further, a little bit closer to what needs to be done. And that's why once we have this initial weights not initialized by random weights, but weights obtained from this pre-training things, then this complex task performs much, much better. Okay, and you can see that once we have this, our results actually, you can see that if you see this F score, just concentrate on this F score, it actually improves 0.4 to 2.60. And what we have done nothing. What we have done, we have just initialized with the pre-training weights rather than start from random. So with same amount of data with all the competing models, we improved more than 50%, or not more than 50%, but also almost close to 50%. Okay, so the point is domain-specific pre-training fine-tuning. So this is called pre-training fine-tuning. So what we have done, so there is this weights. Initially, we are getting from pre-training, and then we are training this system with specific question answers, and we are fine-tuning this system. So this is called a pre-training fine-tuning paradigm. Okay. So domain-specific pre-training fine-tuning model significantly improves performance, but it takes a lot of time, and we know the time drill in various ways. Okay, it takes a lot of time because anyway you have to take the cost of training this 300,000 e-manuals to get the initial weights. Okay, so there is a cost, that there is a lot of time which has been spent. So our next, so I will just elaborate this with the issues that if you see that pre-training on bout, okay, biomedical, this has like 4.5 billion words, 13.5 billion words. So it takes means tens of days, if not months, okay, in various cases. So this is BioBart, which is now an old model, and this is a small model. It took like 23 days on 8 NVIDIA V100. So V100 now is obsolete, but 23 days, 8 NVIDIA V100 GPUs. So it is a huge time-taking models, and say people like us, our universities cannot even support this 23 days. Many times they cannot even support this 23 days continuous training. Okay. So the question was that can we have a compute and data efficient pre-training architecture to solve sentence and token level tasks? So let us step back a bit and think what are the assumptions of masked language model. So masked language model, what was it doing? The quick brown fox jumps over the lazy dog. Okay, and what was it doing? It was masking fox. This was its strategy. So now what is happening? Each sentence and documents hosting them are treated as independent entities. So the strategy there is each sentence is an independent entity, each documents are independent entities. In practice, if you think carefully, this is not so. There are various several documents which are very similar to each other. Okay, like e-manuals of a phone series. So the e-manual, the electronics manual of iPhone 11 and iPhone 12 would be little different, but not much different. So there is a lot of similarities. Or say movie review by different newspapers on a particular movie. Okay, so movie reviews by different newspapers on a particular movie would have a lot of similarities, or scientific articles on preaching. So these articles have a lot of similarity, although there are differences, but there are a lot of similarities. So the next thing we begin to think, can we leverage document level similarity and their categorization for preaching? So next we begin to think, can we leverage? So now see this thing clearly. See, we have document metadata. We have document metadata. So document metadata is something like this. Just a second. Huh. So document metadata is something like this, a customer e-support. So it is a stereo equalizer e-manual. So this is the document metadata. Okay, so stereo equalizer e-manual is very similar to a stereo equalizer e-manual of a different type, but it is different from Blu-ray e-manuals. So this is what we begin to leverage. And also there is another interesting thing. Many of the documents actually follow some sort of hierarchy, and these hierarchies are either given or you can infer. For example, if you think of this e-manual, it is something like an electronics audio player recorder stereo system. So this is a Google hierarchy which you can decipher. This is given in the internet. So this document, stereo equalizer e-manual, follows this hierarchy. Okay, take this scientific domain archive. So this follows the hierarchy of computer science machine learning. For a legal domain, this follows the hierarchy: agriculture, product, subject to market organization, oils and fats. So many of the times the hierarchy is given like the second and the third cases, while you can infer it using some Google hierarchy thing, and you can get a nice hierarchy for each document. So, from a document, we are inferring two things. One is comparison with other documents, another is supervision and trying to understand the document belongs to which category. So, now we are not learning each sentence or each words by say. We are trying to learn the entire document. How does this document look? What are the differences? How this document belongs to which category and which hierarchy? Okay. So this is how we say, and we have two losses. One is contrastive triplet loss. What is called contrastive triplet loss means these two are similar and these are different. So this is a loss which we calculate, and we have a hierarchical classification loss. So we try to classify a document in the hierarchy, and according to its failure, we give a hierarchical classification loss. So these are the two laws. Previously, what was the loss? It was a masked language model where we were giving the loss if the machine was failing to identify the fill in the blank sentence. Okay. So now with this, we focus on pre-training on various domains like customer support domain, legal domain, scientific domain. And what we do, we take just 2000 triplets per domain used for pre-training. This is negligible compared to current SUTA model. And just for your information, customer support, scientific, legal domain have 4 levels of hierarchy. And if you just expand the tree, you can see the number of hierarchies there. Unique hierarchical options are there. Okay. So with this, we train, but we train with just 2000 triplets. Okay, not more than that. Okay, we just train with 2000 triplets and it gets trained. And what we see, there's a drastic reduction in pre-training. And reduction is huge, like it is like 1300x time. So it is, as a conservative estimate, around 500x reduction in training time. And we work it on 3 domains, 6 tasks, 9 datasets, and we show that there is a modest 1 to 3% improvement even with drastic decrease in pre-training. So although we have reduced the time of pre-training drastically by 500x, when we do the when we do the when we do the fine tuning, the performance doesn't decrease. Rather, there is a modest 1 to 3% improvement. And there is another additional advantage. What is this? This is called catastrophic forgetting. So, what is catastrophic forgetting? Catastrophic forgetting is you have a machine, a pre-trained model. Now you continually pre-train it on some specific domain, like medical domain, and then you ask this pre-trained model, which now has been fine-tuned or has been customized for medical domain, the general purpose questions. Okay, general purpose question is like what is the name of the president of USA? Say a general purpose question. This machine now, since it has become customized for medical domain, many of the times this machine cannot answer or fail to answer the general purpose questions. And this is what we call catastrophic forgetting. And this is a very standard feature, standard thing which happens in machine learning. But what has happened, since we have trained frugally, we have trained with just 2000 triplets. So 2000 triplets has updated the weights of exactly the needed weights, and it has left updating weights of other um, unnecessary neurons, okay, which were not really performing this task. And that's why we avoid catastrophic forgetting. And that is a very important result. Okay, so just to summarize, we have frugal pre-training leveraging document level semantics showing dramatic improvement, and we do on several domains. More domains need to be tested to prove generality, but as you know, you can do it again and again. It is working on various domains. So next is all this we are showing on text data. But what do we do where semantics is not available? Semantic, because in the text data there is semantics. The quick brown fox jumps over the lazy dog. We know D is a word, quick is a word, okay, brown is a word, etc. So if you take non-language strings like genes, then really you don't know. So now this is something which is like you have this gene mask, which is a fast pre-training of gene sequence to enable few shot learning. So now what happens? These genes are like long strings, very, 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 very long strings, and they are like 2 to 4 exabytes of human genome data. This is there. So these are long strings, and they have some, since these are long strings and they have some alphabets also, ATCG, so they can be considered as some sort of strings. Okay, and you can apply the same mask language model on this. So what happens? The basic state of the art, like DNA BART, what they did, they were masking randomly. So this is in the absence of any semantics, what can you do? You can mask randomly. So they were masking the six cells randomly. They were taking six cells and they were masking it randomly. Fine. So they are actually thinking that this is a six-letter word. I am masking it randomly. So what happens if you mask randomly and don't understand the semantics? Take this example, the quick brown fox jumps over the lazy dog. So if you mask randomly, then what will happen? Instead of fox, you may mask N and FO. Okay. So if you mask N and FO, then will the machine learn? Yeah, machine will still learn, but this becomes too difficult for machine to learn. So machine will need more and more and more data and more training if you mask instead of fox N and FO. Or on the other case, if you mask the, so the is a very easy thing. Okay, if you mask the machine doesn't learn anything. So training steps are wasted either on too easy or too difficult predictions. Okay, this is how when we cannot leverage semantics, this will happen. The training steps will be wasted on either too easy or too difficult predictions. Fine. So other example. Other example is like if you take New Year. Okay. So if you mask new, it is very difficult, very easy to tell New Year. So rather not masking new, mask New Year together. Then perhaps you will get some clarity or some sort of understanding or some sort of better training, So what you do, this we can show that using some mutual informations like pointwise mutual informations to identify such frequent co-occurrence. You can use pointwise mutual information to identify such frequent co-occurrence, and once you identify such frequent co-occurrence, then mask the entire column, mask the entire set instead of masking individually one part of that set. Because if you mask one part of the set, the other part would be easily available. And in this way, we do it. We have a modified mask center. We fetch a modified mask centers which mask the entire set, because this entire set or this entire sequence or this entire pattern is repeated many times. Okay, this entire pattern is repeated many times, and in order to learn fast, we need to mask the entire thing so that the machine has a slightly difficult task and machine does that task. Okay, so this was the idea, and with that idea, when we train, we had this basic state-of-the-art model DNA part, which was pre-trained on 120 case steps, and our gene mask was trained on just 10 case steps. And when we perform some few shot setting, when after pre-training we do some few shot setting, we show that for all tasks, this is the improvement from DNA BART and logo, we improve decently from 1 to 3%. And for logo, actually the improvement is much more because it is a smaller model where we improve from 5 to 7%. So the takeaway is, see, they were training on 120 case steps. They were needing a huge amount of steps to ultimately converge. We were taking much less steps, like 1/12 of the set, but ultimately getting the same data. So it is a way of smart learning. So see, if you see your JE days, if you think of your JE days, so there is a typical advice many of the teachers give you, that don't concentrate too much on the sums in the beginning. Say in physics, Don't concentrate on too much on the sums in the beginning, first 10 sums and last 10 sums. Do the sums in the middle because those are relatively straightforward, relatively easy to understand, but also will teach you the concepts very well. So this is how this same thing happens here. This same things happens here. And this is how you have the pre-training model. So the summary is gene mask ensures substantial speed up of 10x and performance improvement over random masking strategy, okay, in a few short settings. So this is a very interesting thing, and we have to incorporate domain knowledge while pre-training needs to be explored. Okay, so now let us. I will skip the crystal part because crystal part is another entire domain, but I will come to another interesting thing. So the next thing is, see what happens if you know all this language models, they have a vocabulary. Okay, they have a vocabulary like bird had uh, 30,000 as vocabulary. Okay, or if you see Llama 2, I think they have Llama 2 or Llama 3 has 1.5 lakh tokens as vocabulary. So they have a vocabulary set. Okay, a vocabulary set, and if your words, if a word doesn't fall into that vocabulary, then what you do, you subtoken it and then pass it on. So say a word medical. If it is not in the vocabulary, then what will you do? You will break it in med and equal or medi and cal and check. Medi is in the vocabulary, yes, and cal is in the vocabulary. Okay, fine. So then it is put it in a subtoken words. Okay. Or in the worst case, what can happen? That it can break down into MEDICAL. So 7 tokens. It can break down into 7 tokens because it is not present in the vocabulary. So now what happens as soon as it breaks down into 7 tokens? So what is this tokenization? This tokenization is context aware tokenization. So context aware tokenization means what? Say bank. When it is written bank would be interpreted according to context. Okay, according to context, that whether it is a money bank or a river bank. So this type of context our tokenization is there. But as soon as a word breaks down multiple times, the context gets diffused. The context gets lost. And as soon as the context gets lost, the performance, downstream performance begins to go down. And when do context gets lost, or when does this happen? When we work on some domains, like medical domain. The entire set is not trained on medical domain. It has been trained on general purpose data set. It has been trained on, say, CNN Daily Mail. I can tell you the CNN Daily Mail, the news data set. So as soon as we work on medical, then it is a different story. Okay. So again, the issues with pre-trained language model is the vocabulary mismatch. So what is happening that the tokenizers used in such pre-trained language model is optimal for tokenizing medical concepts bearing words. Like if you think erythromycin, you don't have a token like erythro and mycin, but you have a token yard, it, hr, ob, sign. So as soon as you have erythromycin broken down in so many tokens, there is a high vocabulary mismatch, and this led to completely diffusing of the meaning of erythromycin. And so this leads to suboptimal tokenization of majority of domain specific words, and where the domain specific words are the discriminating words. If you have a medical document, you can write the person has, say, liver cancer. Okay, so the person has is and liver. Even these five words are really not domain specific word, but cancer is a liver domain specific word. Or say person has myeloma. So myeloma is a domain specific word. Although this domain specific words may be 10%, 20% of the entire sentence, but these are discriminating words. And what happens when there is a vocabulary mismatch? These words lose their meaning because they are subtokenized into various small parts. Okay. So this issue of subdomain organization is further excavated by inadequate domain knowledge. The ill-tokenized subwords leads to poor representation, which I am saying, which then propagates throughout the model. This poor representation and inadequate domain knowledge leads in bad summaries. Okay. So our method, we consider the target task dataset for the task of medical summarization. So now what we do, we build a large scale in-domain dataset. So the in-domain dataset to moderate vocabulary adaptation. So what is happening? That we are doing a vocabulary adaptation. And what is vocabulary adaptation? Say BART has 30,000 words. Okay. Now we will add 3,000 more words or 2,000 more words, medical specific, so that this bird have now 32,000 domain specific, 32,000 vocabulary words, and the medical terms are taken care. Okay. So we propose vocabulary adaptation as an efficient hyperparameter search task using fragment score, how much fragmented it is happening, and we have an efficient hyperparameter tuning. I'm not going into the detail, but the basic idea is that this is 30,000 words BART has, 30,000 words as vocabulary BART has, or 30,000 tokens as vocabulary BART has, and we are adding 2,000, 3,000 word tokens more so that for medical terms, the breaking down doesn't happen too much. Okay, so I'm not going into the details, but when we do this sort of evaluation, you will see that our algorithms perform deep. See, these are very difficult tasks. These are very difficult tasks and very important models. Pegasus is a very optimized model. Even on that, our improvements are like 10%. In many cases, our improvement are like 5 to 10% once we have the vocabulary adaptation. Okay, and it performs better on zero and few shot and helps in high OV concentration. So OV concentration means if you have out of vocabulary words, if you have a lot of out of vocabulary words, then Medfog works good and it helps in generation of longer summaries. If the summaries are long, in those cases, the out of vocabulary words also begins to increase and Medfog comes to a rescue. Okay. So anyway, it also performs with medical LLMs. If you have just medical LLM, so there is another effort that you have medical LLM where you are training entirely on medical, like Med Mistral, Med Alpaca. So this type of medical LLMs, it performs at par with medical LLMs, where medical LLM has been trained entirely on medical data. But what Medwork is doing, it is taking the general purpose thing and just adding 2,000 more words to make it medical friendly, right? So anyway, I would not go here, but one of the important part of pre-training is to alleviate this high vocabulary mismatch, and in this work, we actually alleviate the high vocabulary mismatch. So just to have a final word, So this basic paradigm we have also implemented in time series in graphs. I didn't show the graphs. Okay, I personally believe pre-training is one of the best things which happened in machine learning, deep learning, and that's why we are seeing such a huge jump, huge improvement in performance, huge hue and cry in the society. However, there is a huge scope of optimizing and using it prudently. That this talk enumerates some of the techniques. So again, thanks the organizers for giving me an option to speak, and I am open to questions.
Thank you very much, sir, for the talk. We are open to questions. We have some questions which we have got over Discord. Yeah, Karan, you can go ahead first.
Hello, sir. Thank you for this talk. It was really informative. But so one of the things I noticed was all the pre-training that was mentioned. It sort of concerns around mass language modeling. Right? Why i- is it not possible to do, say, some sort of auto-regressive pre-training? How GPT models are trained?
Yeah, so I didn't show the results of autoregressive models. I didn't only the last thing I was showing that it is performing as similar to medical AI. So I just wanted to keep the talk more informative and more educative so that basic understanding comes. The second thing is in autoregressive models, uh, the what we have noticed the replacing something is much more difficult or adding something is much more difficult because they are trained on so huge data that there is some sort of optimization which has happened. Okay, there is some sort of optimization has happened. So we have results I cannot show you just now, but all these things when we are doing on auto regressive things, the improvements are not as big as this. And this is basically because by the amount of muscle power these autoregressive models have been trained, that it has become optimized at certain points. Okay, so so see again, if you think all these are small hacks, okay, which you understand the system and try to interfere into the systems. If you see the entire talk, it was like you are trying to interfere into the system in small ways. Okay, so those small hacks, which we are still working a lot on that. We have to understand the system more deeply to actually interfere into the system. To be frank.
Right.
Um,
I think that that answers my question.
mhm.
Um, Another question that at least I had was like, are there any results where instead of adding vocabulary for the fine tuning, like fine tuning on the medical domain, like we already add the vocabulary tokens, like from the start and do this joint optimization during the pre-training itself? Are there any results for that?
No, see, this is what is happening. There are work where yours like I showed the medical LLMs, okay, or you had previously made BERT, okay, where they were starting from medical data set. So that way they have a different vocabulary set. But here the idea is from a university setting. Think this from a university setting. You cannot just go and add, you cannot not pre-train a new model from scratch. So then are you just a user or you can interfere in this model? So basic idea is, are you just a user who will use it and be happy and do something, or you will interfere, you will understand the architecture and make interfere according to your capacity. You cannot interfere and make some architectural change which will take 50 days to train. Okay, you are not simply there. So this is how we see it here.
Sure, that answers it. Thank you very much. Uh, Anyone else? They can raise their hand or pick up the questions from the start.
Okay, I think then I can stop presenting. Yeah.
Yes, absolutely fine.
So great. Thank you for inviting me. And yeah. So
Um,
I will be in Indo-ML. If you guys are in Indo-ML, we'll meet.
yes, sir.
Okay.
Uh, One general question we had.
Okay.
So like it was more about like pursuing PhDs and like just masters and higher studies. Like so, one question, like one general question which we always have that when students are usually confused that whether they should go for like work for a few years then go for masters or they should directly go for masters and do a PhD. This because now since industry research has had such a boom recently. So what's your take on this? Like doing academia research versus industry research, how is it
So
in that?
my take on it is long term. If you think it is always good to do, if you are mentally prepared, it is good to do masters PhD all first and then go to industry. Means this is, uh, but people may have their doubts, so people go and do it. But if you don't have doubts, or if you really thinking that down the line I want to do a masters, I want to do a PhD, then do it immediately. So, say PA, why there are various reasons, because if you are in a good group, anyway you will get industry exposure. Not that when you are doing masters, you are just sitting here. You can see even in India, all good PhD students are getting some industry exposure. Either they are working on industry funded projects with their advisors, or they are going for some internship. So this thing is always happening, and this is true in US also. So that way you will not get a industry flavor is not true, at least for computer science. It may be true for mechanical. Some people in mechanical may be doing too theoretical work, and which may not be too much used in industry. But in computer science or AI, luckily this is not true at present. Okay. And second is, if you do a PhD, etc. Say if you are finishing your BTech at 22 and masters you will finish at 24. PhD it will take 5 to 6 years. So you are already 30. So, and then if you think you will build a faculty career, etc., then uh, it's always, if you think you will do that, it is better to do fast because it takes time. But means you have to bear the burn that for 30, till 30 you will be a poor PhD student while your friend may be having a Camry or a Corolla or some Toyota or maybe even a Tesla. That you have to bear. That is fine. It's your choice.
Thank you, sir. That answers my question, please. If anyone else has any questions, they can put it in chat or they can just unmute themselves. Yeah, Karan, go ahead.
Yeah, sure. Another say domain basically. So I saw that there was also some talk about crystal or crystal based pre-training. Is are there networks that do say pre-training on material sciences?
Yeah, yeah. Means I've been working on material science and pre-training and machine learning for a long time. Now for 5 6 years. So that is one project which is interesting and which makes me also learn a lot of things and and so the interesting point is somehow as you saw that this time chemistry means not only the physics, the chemistry prize also went to machine learning. So my experience is there is a lot of scope there, and if you get a good partner who understands that understand machine learning has expectations. See, there are two things. If you have means, all these interdisciplinary partners, there are two types of people. One is who thinks nothing will happen, these guys are wasting my time. Another people thinks that this is the panacea. I had a lot of problem for the last 25 years, these guys will solve it. None of this is true. So of these interdisciplinary projects fall through because their expectations are not well set. But if the expectations are well set and people begin to understand, okay, these guys are not God coming here and will solve all the problem, but they can solve some of the problem, then things becomes very interesting. Luckily, I have good collaborators who are helping me with this. And I really enjoy working on crystals. And we can talk more about this. Maybe when we meet in person, we can talk more about this.
Thank you for that answer, sir. Still have some time left, so if you have any questions, feel free. Otherwise, I'll continue with some general questions which we received over Discord. Okay, before I answer the question, I had a question myself. So you mentioned that usually it's noticed that after you do the pre-training and you do a fine tuning on your whatever domain specific data set, there's a loss of the general semantic understanding of the natural language which you have already pre-trained on. Like, and I see this as something analogous to something like model forgetting, like you're forgetting certain things which you have learned over the time. But how is there any way that you can combat that when you're doing the fine tuning, like to avoid that, or maybe?
There is no so catastrophic forgetting is a problem, right? So there is no explicit way of uh, tackling this. I at least don't know so explicit ways of tackling this. So there are various things people have proposed, like curriculum learning. So you learn easy to difficult, so that you don't you learn system, because here you are not learning very systematically. You are learning whatever is coming. You are randomly learning. So that is one part people are proposing, and then other part is when you are relearning or means continually training, how to can you not touch all the weights. So this is important. That so this part still I think there is no clarity within the community. There is no clarity within the community, but people are trying it in various ways. So see, LoRa, etc. So LoRa, one point is LoRa is making it low ranked and making it efficient. That is one thing, easier. But other thing also comes that it can prevent a little bit of catastrophic forgetting. It doesn't overtrain, means what we call as overtraining. So it has its utility. Mostly the utility is easy training, but also it can offset some of these bad points.
Thanks a lot. Answers my question. I'll go with the general question next. So this was basically about doing research in undergrad, because at least till a long time it was about how like most of the research was mostly done by masters and PhD students. Very recently, it's having happened that undergrads are also starting doing research. So what are your suggestions or recommendations to a person who is just starting out research in ML as an undergrad? How should they reach out to profs? What things they should do so that it will help them to make a career out of it?
So, as for the undergrads, I would first suggest that research is secondary. First, you should concentrate and do your coursework. So, this is very important. I see many people uh, trying to build CVs, talking with 5 professors, doing 5 projects, and putting that in CV. Ultimately, nothing happens. So, but that is very important, that many of the time people are too concentrated, is as good, but concentrating too much on building CVs is also not very good. And all the people are smart enough so they can see through. So it's not that people cannot see through. So this is important. Second is, means you can have an initial initial seeking that you can seek two, three professors, talk with them, try to do a small project. But at certain point, you should stabilize and do one project, even if that is not optimal. I understand you when you go to back to your hostel, one of your senses say, I am doing so cool work, and you feel, I am doing such a drab work. Maybe I am doing data collection entire day, and this guy is telling he is doing so cool work. So then I understand the peer pressures well, but you have to concentrate on one or so the good thing about undergrad or the good opportunity about undergrad is you don't have the pressure of failure. Okay, as a PhD student, if you fail, your paper gets rejected, you have a huge pressure. So that is not there. So the most important thing is working on one project. I think, see, if you start from second year you search, but third year you concentrate, work with one professor. In one semester, you will understand if the professor is okay or not. Because he may have technical difficulties, etc., but he is a person, he is a kind person. He has a decent group. The PhD student with whom you are working has decent knowledge, and they are hearing you. If that is there, concentrate and do it for 2 years. That would give much better results. Maybe 5 years down the line, you will think, what stupid things I have done this 2 years. That is fine, but it doesn't matter. Uh,
Thank you, sir, for that. I think we have time to take one last question if anyone has it. Thank you.
Anyway, it was great talking with you guys. So this is the thing which you are organizing for the first time, or
No, sir, we have also organized it before. So it's like a student club, which is just like interested in ML side of the things. So our seniors organized it last year. Their
no?
seniors organized it the year before that. So
Okay, then I think
thank you very
yeah.
much. Thank you
Thanks
very much, sir,
for
for
having
agreeing to
me.
join here on the early weekend morning. We understand
No,
that you
no,
also have your
fine.
own plans.
I
This
at
was
least have
really, really
some work
informative.
in the weekend, otherwise I would have slept. Yeah. Okay.
Thank you so much, sir.
Bye.
Thank you.